Good evening, everyone. We are in the week 7 problem solving session of the NPTEL course Network Analysis, and week 7 is about network theorems. I am Teja Golla, a fourth year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, EE Department, IIT Kharagpur. Let me share my screen. Okay, and one thing I always kept telling you is try to go through the lectures, because this session is mainly problem solving session. Although I cover some of the concepts, it is just like a summary rather than teaching again. So it would be much clear, or it would be clearer for you if you go through the lectures before attending this session. So this week it's all about network theorems. So we have learned a few like analysis, like mesh analysis, nodal analysis, and then we have tried to learn how to solve a problem using a linear differential equation. Then we have also seen how to solve them using phasors. Then last week we have seen Laplace, how to solve any circuit using Laplace transform. And this week we'll be discussing about network theorems. So how what network theorems are available, which you can directly apply in certain cases, so that it will save time and you can directly get to the answer. And they will be helpful because they are just a results which you can directly apply. So we'll start with the substitution theorem. So I'll just quickly go through theorems. I'll not go in deep, but I'll just explain what those theorems are, so that when we solve problems, it will be clear. So substitution theorem. So what this theorem says is, say if we have any impedance or say resistance, that can be converted into a voltage source, or it can be represented as a current source. So what we are saying is, say I have a resistance. Okay, say the resistance is R and the value is I. So now this can be represented by a voltage source also. So I can convert this into a voltage source. Now the voltage source value will be IR, and the polarity will be the same. We should not mess up the polarity because current is flowing from left side to right side. Left side is at a higher potential. Now this can also be represented by a current source. Okay, and the value of the current is I. And the direction of the current should be same as the original case. So basically, if we see the current that is flowing through this will be I, and the polarity voltage value is IR. Similarly, the potential across this will be IR. So that none of the theorems will be violated. Like KCL theorem should not be Kirchhoff's current law or Kirchhoff's voltage law. Neither of them are violated. If you see, the voltage across the original element is IR. In the second case also, the voltage is IR. So KVL is valid. In the case of third case, we are replacing the original resistance with the current source. So KCL is also valid. So basically, even if you apply KCL or if you apply KVL, it should not be violated. Is it clear? It's a very simple theorem and straightforward. We are just transforming the element into either a voltage source or a current source. Depending upon our ease, we can do this so that things can be simplified. Not every time, but whenever it is needed. Any doubts in this? Okay. So then we'll go into Thevenin's theorem and Norton's theorem. Although I'll not cover the proof, I'll just cover what this theorem is about. So I hope everyone is clear with the substitution theorem. Okay. So the Thevenin theorem says that any.
Sir,
Yes.
that substitution theorem, the second
Yes.
diagram is understood, but the third one, you have mentioned that arrow mark that indicates
Yes.
only the current source.
Yes.
Then how can we represent R, sir?
So the current value is I. The voltage across the current source is IR, because the original voltage is IR, right? So if we consider this as terminals A and B, so if I represent this as terminals A and B. Between A and B, a current I is flowing and the voltage of VAB is IR. So in all the three cases, it is valid. In the first case, VAB is IR, current is flowing I. In the second case, VAB is IR, current flowing is I. In the third case also, VAB is IR and the current flowing is I. So we are not violating KCL or KVL, but we are representing it in a different way. So the voltage is IR,
Okay, sir.
current is I.
Understood, sir.
Okay. So in Thevenin's theorem, what it says is any linear network, not completely. Someone mentioned something. Good evening, sir. Yeah, Gnanendra, good evening. And I am hoping that everyone is getting benefited from these sessions and they're doing well in the assignment. So we were discussing. Sir, source with internal resistance R, sir. Yes. So if you have a source with internal resistance R, then it cannot be represented by this, because here what we are doing is here we are considering a source without internal resistance, because if you consider source with an internal resistance, then what happens, the entire value will be I capital R plus I into small r because of that resistance, then the KVL will be violated. So a resistance can be replaced by a ideal voltage source and this also ideal current source, so that none of the KCL or KVL will be violated, but you cannot add any series resistance, then this will be violated. So ideal voltage source and ideal current source only. Okay. So Thevenin theorem says that any linear network with multiple voltage sources and current sources can be represented by a voltage source the value is named as VTH, Thevenin, in series with an impedance, which we call as Thevenin impedance. So basically what it is saying is, say, let us consider one linear network. And it might have some sources. This is I1 and this is I2. And it also has some voltage sources, current sources. So V1 and V2. And this is a linear network. Yes. Sorry.
What is the difference between network and circuit, sir?
Both are same, like it's a different name. Network is just same as circuit as well. A linear circuit or linear network, both represent the same.
Okay, sir.
So now we have a load. We have a load, say ZL. Okay, and the terminals I'm naming it as A and B. So now the entire circuit that is connected to the ZL, so that can be represented something like this. Maybe I should use a different color for this. Let us use blue. Blue is your blue, so light blue is light blue. And this is ZL. And this is ZTH. And then VTH. So this circuit on the left side, we are just simplifying. So if we draw Basically, whatever is there here, this thing we are representing into what is there on the right side in the light blue color. So the Thevenin's theorem says that this linear network with multiple voltage sources can be represented by a voltage source V Thevenin in series with an impedance Z Thevenin. So if you have a complex network and then if they're asking what is the voltage of VAB, then we can calculate VTH, ZTH and then connect them in series and then solve the circuit which is on the right side. So then now let us not go into the proof because that sir has covered. So we'll discuss about how to calculate this VTH and ZTH. So if we think about VTH, which is called the Thevenin voltage. So how do you calculate Thevenin voltages? Thevenin voltage is the open circuit voltage at the load. So once you disconnect the load, okay. Now what is the voltage that you are getting? This is VTH. So once the load is disconnected and calculate the voltage VTH at that terminal, then that open circuit voltage is called the Thevenin voltage. And how do you calculate the Thevenin impedance, which is what we are calling ZTH? So how do we calculate Thevenin impedance? So for calculating the Thevenin impedance, first you have to remove all the sources. When we say removing the sources, it means current source will be open circuited or short circuited.
Once again, sir.
When we like say removing the sources, say in the case of superposition theorem, when you connect multiple sources, you will consider one source at a time. So when you have to remove the other sources, say for current source, whether we short it or open it.
Open circuit.
Open. And voltage source?
Short circuit.
Short
Short
circuit.
circuit, yes. So that is what we are doing. Voltage short circuit, current open. Yeah, Dhanendra, you are right. So which is what we are doing. So first, we are not connecting the current source and we are short circuiting the voltage source. And of course, load is not there. Now, calculate the net impedance across these two terminals. As if say, we are seeing from this, from this terminal, what is the impedance that you see from this terminal? Meaning, I'll just give you a simple example. Say, this is our circuit. Okay. So this is my load. So now what we are saying is first we'll short circuit this voltage source. So this resistor is of no use.
Sir.
And yes,
Voltage source cannot have parallel resistance. No, sir.
why?
At least, if it has parallel resistance, it should have series resistance.
Why so? Like why
I'm
is
asking why it should be because voltage. We are adding resistance to slow to reduce the current value, sir. Here, voltage can't be reduced if resistance are in parallel.
no, I'm not getting why we cannot connect resistance in voltage in parallel with the voltage source. Like, did you read it somewhere or any
Can't
reason?
be, Voltage can't be divided in parallel, no, sir.
But that can be divided, but what is the reason that we cannot connect resistance in parallel with the voltage source?
Voltage can't be divided in parallel resistors, no, sir. So that.
But okay, that is okay. Voltage cannot be divided, but why we cannot connect? Like, is it that you said you cannot connect, right? Like, why we cannot connect? Like, what is the issue if we connect?
Sir, I'm asking whether we can connect or not. We cannot.
No, we
I'm
can connect. There
asking
is no issue.
because resistors are connected to reduce the value of source, no, sir. Here, if we connect in parallel, we can't reduce the value.
No,
If
that is one
we should
application of
connect,
the resistors where you step down the voltage, but it does not always mean that any resistor that you connect, it is just to reduce the. This is some circuit that is given. Like it may be helpful in practice or maybe not helpful, but it is just circuit. Like every circuit doesn't mean it is applicable for some reason, right? It is just some theoretical circuit. If you connect a resistance across the voltage source, the voltage across the resistance is fixed.
okay.
Okay. So now in this case, for calculating the Thevenin impedance, first we'll disconnect the load and see the impedance from these terminals. Okay. So this is my R1, this is my R2. Because voltage is short circuited, that resistance will also be short circuited. So now the effective resistance is seen between these two terminals. This is R2 and this is R1. So ZTH across these two terminals is nothing but R1 parallel R2. So that's how we find Thevenin impedance. So is it clear or any doubts like how to calculate Thevenin impedance? First, we have to remove all the sources, which means short circuiting the voltage source, open circuiting the current source, and across the load terminal, we'll find the Thevenin impedance. Those two terminals.
Clear, sir.
Okay. So this is the Thevenin's theorem. Similarly, we can discuss about the Norton's theorem. So for Norton's theorem, I'll just copy paste because there is so much similarity between Thevenin's theorem and Norton's theorem. Okay. So we'll use a different color for Norton's theorem. So any linear circuit with multiple voltage and current sources can be represented by a current source here. Instead of voltage source, we'll get current source. And because it was named after Thevenin, this is named after Norton. And not in series because it is current source, it is in parallel. In parallel with the impedance, Thevenin impedance and Norton impedance both are same because we calculate in the same way. So only the current source in parallel with the same impedance. So now what we are trying to say, let me just copy this diagram.
Sir,
Yes.
what are the applications of these theorems?
Okay, just a minute. So like application in the sense, say, uh, like one few applications will be in the like transistor, but say in this linear network, only passive elements are there: resistor, capacitor, inductor, and you have access to this voltage source and you have access to this current source, which are externally connected, right? So now this complex circuit is connected to some load, whatever load we have. Now, say my objective is to see the characteristics of this load, but I don't know what is inside this, right? So then how am I going to like convert this into a simplified circuit? So in that cases, when you know that inside this linear network, it is only passive elements because the sources are externally connected, then you can apply this Thevenin's theorem or Norton's theorem to simplify this into the circuit. So like whenever a complicated circuit is there where you cannot physically visualize anything, like because from the circuit, it would be very difficult to visualize what is happening. But from the circuit, it's a simple circuit where you can see things, right? Then like it will be easy for you to understand. Or there is one application like which is very famous. Say I want to uh, maximize the power that is being transferred to this ZL. Like I have a network. Now what should I be connecting at ZL so that my power transferred to this ZL will be maximum? So in that case, how will you know? From the circuit, it would be difficult to find what is the value of ZL so that my maximum power will be transferred, right? But if you convert this into this circuit, say Thevenin equivalent circuit, when you have two impedances in series, there are few results. Say if this is resistance R, then the load should also be equal to R for maximum power. So then I know that my ZL should be R so that the maximum power can be transferred. Similarly, if this is R plus j omega L, then this should be R minus j omega L for maximum power transfer. So for applications where you want to maximize the power transfer to the load and you have control over the load, then you have to find this Thevenin impedance so that you can set the load in such a way that the maximum power can be transferred. Also in circuits where complex network is there, in order to analyze, you can convert that into simplified Thevenin impedance and Thevenin equivalent and Norton equivalent to understand or see the working of the circuit better. Is that clear? Whoever
Yes,
has
sir.
asked. So this is a current source. So it is I Norton, and here we have ZTH. This is I Norton, and this is ZTH or Z Norton. Both are same. Now this is the Norton's equivalent, and this is the Thevenin's equivalent. So if we write, this is Thevenin's equivalent circuit. Thevenin's equivalent, and this is Norton's equivalent. Okay. So now how to find IN and how to find ZTH. IN we'll discuss, ZTH is already discussed. So let me just copy paste this thing. Okay. So instead of VTH, we have I Norton, and this is called Norton current instead of Thevenin voltage. So we have I Norton, and which is called Norton's current. Right. Norton's
Sir,
current. Yes.
instead of finding IN using Norton's circuit, we can find by VTH by ZTH, no, sir?
Yes, you can also do that. Yeah, it was a good point. I was actually about to tell after this. Yeah. So there is a relation between this circuit. If you see this circuit as well as this circuit, both are actually same. Okay, I'll also cover that aspect. Okay, I'll come. So yeah. So in the case of Norton current, we will short this because in the Thevenin's equivalent, it was open, and we are finding the open circuit voltage. Here in the case of Norton, we are finding the Norton current. So we short it. So we short it and then find the Norton current. And there is also a relationship between Thevenin voltage as well as Norton current. So Control C. So this is our Thevenin's equivalent. This is our Norton's equivalent. Right. Agree?
Yes.
This, yeah. So now there is a relationship between I Norton and this ZTH, so the left hand side, which is VTH by, so Norton current, like you can calculate from either way. So I Norton is nothing but V Thevenin by Z Thevenin. So you might ask, like, how can we derive this? So if both the circuit represent the same, then the load current should be same, right? So this load current should be same. Say this is my IL, this is my IL, both should remain same. So can anyone tell me what is IL in the first case?
VTH by ZTH.
VTH by?
ZTH.
Only VTH by ZTH.
TS plus JL, ZL. Sorry.
Yes, by ZTH plus ZL, right? Because there is this is the total impedance. So now here in this case, what is the IL in terms of I Norton? Anyone? Anyone? I in terms of IN, ZTH and ZL. What is the value of IN?
IN into ZTH by ZTH plus ZL.
Yes, IN into ZTH by ZTH plus ZL. So now if I see, both are actually same quantity. So if I compare this, VTH should be equal to I Norton into ZTH, or I Norton equal to VTH by ZTH. So as both the circuit represent the same circuit, the load current will be same. So equating the load current, we can get the relationship, which is also what we have written over here. Fine.
Yes, sir.
Okay. So this is Norton's theorem. So till now we have considered substitution theorem, Thevenin's theorem, as well as Norton's theorem. So we have three more theorems. Before we proceed further, I'll just quickly tell. Any doubt until this?
No, sir.
Okay. So next is compensation theorem. Again, I'll not tell the proof. I'll directly go to the result so that proof, because proof is already covered. So compensation theorem says, say if a circuit has some impedance Z, and now I have changed Z to some Z plus delta Z. So initial current that it was carrying is I. Now it has I plus delta I. So how can I calculate that change in the current? So this can be calculated using an equivalent circuit. So let me just state the compensation theorem. So in a circuit, an impedance Z is carrying I, current I. Okay. So now the impedance is changed to Z plus delta Z. Okay. Now the current I plus delta I, comma, the delta I can be calculated using the following circuit. Okay. So let us see how. So let me first initially draw the original circuit. Say, yeah, let us consider this as the original circuit. Instead of ZL, we have Z. Okay, so instead of ZL, we have some Z. Okay, now this Z has been changed to Z plus delta Z. Okay, so now the current initially, which was I, now it has changed to I plus delta I, and the aim is to find delta I without solving the entire circuit. So now this delta I can be solved from this equivalent circuit where all the sources will be removed. Where all the sources will be removed. So when we say sources are removed, current sources is open and voltage sources are shorted. So current sources are open and voltage sources are shorted. And instead of load, we have one voltage source and impedance. So we have an impedance and we have a voltage source. Okay, and in the effective circuit, the current will be delta I, and then the voltage, this impedance will be Z plus delta Z, and then this will be I delta Z. So this is the equivalent circuit where you have to solve for delta I. Here you have to solve for delta I. Say some question is given where impedance is changed to Z plus delta Z. Find the delta I. So then you have to consider this equivalent circuit and kindly check the direction of the current and the polarity of the voltage source. You have to follow the same polarity. Wherever the current is entering, that terminal will be positive inside in the voltage source. So in this right circuit, Z is known, delta Z is known, I is also known, delta Z is also known. So only unknown is delta I. So you can directly solve this circuit for delta I, and it is very simple, like because other voltage sources are removed rather than solving the original circuit entirely again. So compensation theorem says that if there is any change in one of the element by some delta Z, then the current in that will also say suppose changed by delta I. For calculating this that delta I, there is this equivalent circuit which you can use to directly calculate for delta I rather than solving the entire circuit again. Is that clear, or any doubts? These are just theorems and I am just stating them.
Yes, sir.
Okay. So next we'll go to Tellegen's theorem. So in Tellegen theorem, something called graph will come, a name graph, and we'll go in details of the graph in the upcoming weeks. So graph is nothing but like a circuit represented using branches, currents, and voltages a particular way. The details will go further in the next week. I think it is in the next. But currently, like I can maybe probably state it. So there is less than a minute. If this meeting ends, kindly join back so we can continue our discussion. So if a network is replaced, like if a network is down by replacing the branches by straight lines and nodes by some bullets. So it's a network drawn by replacing elements by straight lines and nodes by bullets. Okay, someone has mentioned. Okay, someone has mentioned, sir, could you please share your reference book? Yes, so earlier also one of the student has asked some reference book. I have mentioned it. I'll put the link in the description once I upload this video. So whenever I upload this video, I'll also add the link of that reference book or the name of that reference book. So you can click it and then you can access it. Is that clear, Parvatam?
Okay, sir.
Okay. So like graph in the sense, say we have some circuit. The details will go in the next week, but this is just a theorem. Say I have a resistance, here some voltage source, here also some resistance, here some resistance and voltage source. here one resistance. So this will be directly represented by lines instead of voltage source. So this will be easy to solve. So it will be represented by straight lines, and we'll also draw the currents direction, and also it will write the polarity in that. Okay, so these details we'll discuss in the further lectures, but let us assume that we have a graph already. How we are drawing, what are the conventions that we are not discussing in this week, but we are just assuming that we have drawn some circuit in terms of the graph, that it is given, and like you have that information. Now, let us considering. So, first of all, this Tellegen theorem, what it says is, say we have two identical graphs. So, two circuits having the same graph, then only this Tellegen theorem is applicable. So, let us consider two different circuits having the same graph. Let me just quickly draw. So, whenever we draw graph, we have to mention the nodes by these bullets, and then we also have to mention the polarity of the voltage in that branch, and also the direction of the current. But when these two are different networks, this is network 1, this is network 2, and both are having the same graph, means direction of the currents, everything remains same. So, but may not be, current may not be the same, but the direction, polarity, the shape, everything remains same. Say this is my plus minus V1. So this is plus minus V2. This is plus minus V3. This is plus minus V4, plus minus V5, plus minus V6. So if a current is flowing from terminal A to terminal B, obviously terminal A is at a higher potential. So accordingly, I have put the voltage polarity. So now here we have the same, but it may not be V1. It is V1 dash, plus minus V2 dash, plus minus V3 dash, plus minus V4 dash, plus minus V5 dash, plus minus V6 dash. Say the current here is I1, I2, I3, I4, I5, and I6. Whereas here currents will be I1 dash, I2 dash, I3 dash, I4 dash, I5 dash, and I6 dash, because both are not same. Then what does this Tellegen's theorem says? Tellegen's theorem says that summation of say k equal to 1, and both of them having say n elements. Here they have 6 branches, but say n. Then it says the voltage of the product of summation of product of the voltage of the first branch with the current of the second branch is equals to summation of vice versa, which is voltage of the second branch, current of the first one. This will be equal to 0. So this is what the theorem says, although we will not get into the proof. The voltage of the first network multiplied by the current of the second network, and then summation of all those terms is equal to 0. Similarly, voltage of the branch in the network 2 multiplied with the current in the network 1, and the summation of all these terms will again be equal to 0. This is what the theorem says. Let us not get into the details of how it has come, but any doubts in like whatever I have explained, like this theorem, like any confusion in the theorem as such, once we get into the problem, then you will understand it better. But till now, you just have to understand what is the result, what is the terminology, what is the convention, which corresponds to what, only those basic details. Okay, someone has mentioned clear. Okay. So now we are going to the last theorem that we'll be discussing in today's class, which is the reciprocity theorem. What does it say and what does it mean? So what it says, So it says two things. A network, first of all, let me state it. A network is said to be reciprocal if the ratio of response to excitation remains unchanged, even if interchange, response, and excitation. Okay. First, the very first question is, what is response? What is excitation? Okay, we'll get into this. But the important thing that one should notice is response and excitation and the ratio of response and excitation. So let us again here in the previous theorem, we have learned something called graph, which we'll discuss in detail in the upcoming classes. Similarly, here we'll discuss something called two-port network, which also we'll discuss in detail in the upcoming weeks. But what is a two-port network? Basically, it has two ports. One is the input port, one is the output port, and any port can be used as input and output. Yes. Uh, yeah. Chandrasekhar, you are right. Input and output. Response is output. Excitation is input. Yeah, very good. So basically, we have something called two-port network. Say we have a two-port network. Basically, the name says it's a two-port network, right? Okay. And for example, the ports are port 1 and port 2. So this is port 1 and this is port 2 on the right side. This I'm calling 1 or say AB. This I'm calling A dash B dash. So whenever you are giving some input to the port, input to the circuit, that is called excitation, because you are exciting the circuit maybe with a voltage source or with a current source. Say I'm exciting it with some voltage V1. Okay. And this current may be I1. Okay. And then on the other side, I am getting the response. So once you are exciting, this here we are calling excitation, and this is called response, because we are exciting it at one terminal and the other terminal we are seeing the response. So this automatically becomes the excitation, which is the input port, and the other port will become the response, because that is the output port. So once you are doing this, then on the other side, which is this output side, A dash B side, B dash side. So here we are exciting it with the voltage and short circuiting the other terminal. Okay. And currents are always inside. Say this is my I2, I1, and this is my I2 dash. Okay. So now the response ratio of response to the excitation, which is I2 dash by input is V1. Now what we'll be doing is we'll be doing the other way around. So now we'll excite, because they are saying the X ratio of this will not change even if you interchange the response and excitation, right? So now what we'll be doing is we'll interchange. Okay. But by interchanging meaning is we are now exciting with the current source, right? So now let us excite it with some current source I2. Okay. So this is my, or let us change the naming. Say this is I1, I2. So I2 by V1 is equal to, here the current is I2 dash that we are exciting. This is my I2 dash. And now the open circuit voltage. So the current here is 0, but the voltage is V1 dash. Okay. So the ratio So now what happens? The excitation will come here and response will come here because we are exciting on the other terminal. So basically, even if you interchange the excitation and response, the ratio of response to excitation, it will be the same. So I2 by V1 will be same as V1 dash, sorry, will be same as I2 dash by V1. So this is what the reciprocity theorem says. So if this network is reciprocal, then you have to find the ratio of the response to excitation by exciting it with different terminals, and then we have to see whether the ratio remains same or not. Is that clear?
Sir, I2 should go from A dash to B dash, no, sir?
Yes, but it is an input. Okay, maybe I'll just give the sorry. So the polarity should be considered like this. Say the original circuit is something like this. So the polarity remains same.
Sir, this equation becomes I2 dash divided by V1 dash.
Yeah. Okay. Thank you. So this is the polarity. So currents are always entering and top terminal is always positive. This is the like polarity that Sir has considered and we'll follow it throughout so that we'll not make any mistake.
Then which is excitation and response? If both has
So this is
sources.
like the polarity. Now, this is in general. Now, here we are giving excitation here and we are checking the response here. Similarly, on the other side, here we are giving excitation and here we are checking the response. So basically, excitation is the input and response is the output because it is two-port network. Any port can be input, any port can be output. But these are the like the convention that we have to follow so that we'll not make any mistake. Because if I consider I2 entering in one, leaving in the other, I'll get a minus sign. So that in order to avoid any such mistakes, we are fixing the polarity. Or you fix another polarity and follow the same. But rather than using some other polarity, we'll use the polarity that Sir has considered in this course and follow the same.
Sir,
Sorry.
in the first circuit, we are doing V1 as a excitation and response I2. So response by excitation will be
Sorry,
I2
I
by
think,
V1.
sorry. I think I have confused you. This should be also voltage and here it is current. I'm sorry. So excitation remains same, right? So this, I am exciting this with a voltage. So V2 dash and then the current here is I1 dash. So now the response is I1 dash. I'm really sorry. Yeah, thanks for correcting. So here I'm really sorry. So we are exciting it with a voltage and we are checking the short circuit current. So this is my response, which is I2, the ratio with V1. And here we are exciting it with a voltage V2 dash and this is I1 dash. So this is I1 dash by V2 dash. Or you can excite with a voltage source and open. So there are like you can excite it with a current source, you can excite it with a voltage source. But here I have considered one such scenario. So we are exciting it with the voltage source and short circuiting the other terminal. Is this clear? Yeah, thanks for pointing that mistake. Clear. So any doubts, anyone, before we go to problems? No doubts? Everyone? Okay. I assume no doubts. Clear. Okay. So we are going to problem solving session. Okay. So all of you just read the question once, then we can solve it. Let me know once you have read the question. Have you read the question? Someone mentioned in the chat. Yes, sir. Yes, sir. Okay, so I'll again read it out. So they have one linear network, same linear network, and they are doing different type of excitation. And they have connected 1 ohm resistor in the other case. So now they have given the values of V1, I11, and I12. Now they are exciting with V2 voltage V2, and they're asking what is the value of I21 of T. And then they're saying use Tellegen's theorem, because they have said that use Tellegen's theorem and in Laplace domain and find the value of A, B, and alpha. So first we'll see what is Tellegen theorem. In the Tellegen theorem, we have seen that if both the network have the same graph, and here they're using the same circuit, right? So the graph is same. And in that case, the voltage of the first multiplied by the current of the second, and the voltage of the second multiplied by the current of the first, the summation is 0. So voltage here into current here plus voltage here into current here equal to 0, or this equal to this, that will do. But very first important thing is to fix the polarity. So this is our question 1, and we'll fix this as our polarity. So we should not make any mistake. So that's why polarity is very important. Okay, so this is the polarity. Voltage is plus at A, here also plus, and the current direction is this, and current direction is this. Both are entering. Okay. So first we'll use the Tellegen theorem, and they're saying in Laplace domain. So let us convert the, yes.
Sir, the summation is 0 or both the terms equal sign? In the theory
Equal
part,
to 0, as well as this is equal to 0, this equal to 0, and these two are equal.
oh, okay.
Okay. So let us start from here. So the first network we are calling without dash, and the second network we are calling with dash. First they have said use the Laplace domain. So let us convert it into Laplace domain. So we have sigma k equals to 1 to n. And I have told Laplace domain means capital Vk of s into ik dash of s is equals to summation k equals to 1 to n Vk dash of s into ik of s. Okay. So without dash means it is the first circuit, with dash means it's the second circuit. So basically we will be dealing this voltage, this current, and this voltage, this current. So let me just first write the polarity so that we will not make any mistake. So this is plus minus, this is the direction of current, this is the direction of current, this is plus minus. Similarly here, this is plus minus, this is the direction of current, this is the direction of current, this is plus minus. So the voltage of the first network multiplied by the current of the other network. So V1 will be multiplied by I21, right? Agree?
Sir, you took Reciprocity theorem, equivalent circuit, Nelson.
Yes, this circuit. But I'm saying that the polarity should be the same for both, right? So I have considered this polarity itself, and then I'm considering for both. Because in the case of Tellegen's theorem, what I have told is the first circuit polarity and the second circuit polarity both should be same, right? So I am free to consider any polarity, but I have considered this polarity so that it will be constant, and like whenever you see two-port network, you will remember this. Because why to consider a different polarity for this circuit and for two-port to consider this polarity? That will be confusing, right? Because it looks like a two-port, I am fixing this polarity and I'm also using it here. But you are free to consider any other polarity, which I don't recommend because that will be more confusing.
But I12 of the is leaving the side.
Sorry.
I12 of the is in opposite direction.
So I want this current. So what will be this current in terms of I21 of t?
Minus.
Yes, exactly. So that's what where we'll commit the mistake if you don't mention the polarity. So that's why I have specifically mentioned the polarity. Clear?
Yes, sir.
Okay. So now what we'll be doing is this is one branch, this is another branch. So voltage of the first into current of the second, which is V1 of S into minus I21 of S. So we have V1 of S into minus I21 of S. Okay. This completes one branch. The other branch voltage is 0. So it is 0. Coming to this, the voltage of this into the current of this plus the voltage of this into current of this. So first of all, here as the current is entering, this is plus, this is minus, right? The voltage here is I21 of S into 1 ohm, right? Agree? The voltage across the resistance. Because I need this voltage and current is entering, means this is positive, this is negative, right? Clear or any confusion? Hello.
How zero?
Sorry.
How is zero, sir?
Because this voltage is 0, right? This voltage into this current, right? This voltage is 0, it is shorted.
Shorted current will be have infinite current.
No. You see, you are confusing many things. If it is shorted, what is the voltage?
Zero.
0. First of all, the theorem says voltage of the first network multiplied by the current of the second network. So voltage of the first network is 0 and current is, here there is some current, right? Which is what
Yes, sir.
they're saying, like this current, which they have not given because this is 0 directly. Now we are going to the second side, RHS side, which is Vk dash of S into Ik of S. So the voltage of the second network into the current of the first network. So the voltage here is what? I into I21, right? Across this resistance.
1 into I2.
Sorry, 1 into I21, yeah. So it is Vk dash is I21 of S. And this is the voltage into 1. So no confusion. Voltage into current of the first branch. Current of the first branch is in the same polarity. So I11 of S. Plus the other branch voltage. So the voltage here is V2. So V2 of S into
Minus I11 of S, no, sir.
Y.
No, sir. Yes.
Yes. So V2 of S into, so V2 of S into this current, right? So now what will be this current? this voltage into this current, right? So what is this current? Red color that I have shown.
Minus I12 of S.
Yes, minus I12 of S. So into minus I12 of S. So this is the expression that we have. Now, what we have to calculate is I21 of S. So bring all the terms I21 of S in this side. So we have I21 of S. Sorry, which one we have to calculate? I21 of S, right? Yes,
So
I21 of S.
while we are taking Laplace transform for the voltage source, we have used the V1 of S divided by S. Isn't it, sir?
Yes, yes. So V1 of S will be 10 by S. You are right. So we'll get back to that. But first I'll reframe this. So I21 of S, I'll bring this side and like basically what I'm trying to do is I'll take this term to RHS and I'll bring this term this side. So if I do that, on the LHS we have V2 of S into I12 of S is equals to I21 of S, I'll take common into V1 of S plus I11 of S. Agree?
Yes,
Basically,
sir.
yeah. So now let us go one by one and write. So what is V1 of S? Laplace transform of V1 of S?
Ten, sir.
10 by S, right?
Yes, sir.
There is one by S term. And then I1 of T. So I11 of S.
2 by S plus 4.
Yes, very good. And then I12 of S. Same, right? Similar.
Yes, sir.
Yes,
How
sir.
much? How much?
8 by
S
S
plus 4.
plus 4.
Yes, Nandini said 8 by S plus 4. That's right. So it is 8 by S plus 4. And then what is V2 of S?
5 by S plus 8.
Yes. I will explain some. So now we have to substitute this. So let me just copy paste all this. So we have to substitute it here. V1. So you please proceed. You do be ahead of me. I'll slowly explain. Don't rely on me for calculation. Shamta, you should do quickly and check whether you are making any mistakes or not. So what we have to do is we have to substitute one by one and then calculate for I21 of S. So my unknown is this, which I'm marking with the red color. So we have to find this. So first I'll substitute V2 of S. So V2 of S is 5 by S plus 8 into I12 of S is 8 by S plus 4 is equals to I21 of S, which is my unknown, into V1 of S is 10 by S plus I1 of S is 2 by S plus 4. So now if I simplify this, I'll get I21 of S into 10S plus 2S, which is 12S plus 40 by S into S plus 4. Agree? So now S plus 4 will get cancelled. So I can do some cancellation. So this S plus 4 will get cancelled. Then I can get I21 of S equal to 40 S by S plus 8 into 12S plus 40. So now what I'll be doing is I'll divide this by 12. I'll also divide this by 12. So then I'll get 3.333 s by s plus 8 into s plus 3.333. So this is my I21 of s. So now can anyone tell me how to convert this into partial fractions? So what will be on my right RHS side? If I use partial fractions, what should I be considering?
Sir, A divided by S plus 8
Okay.
plus B divided by S plus 3.33.
Yes, very good. A plus B by S plus 3.333.
Then you can multiply and compare the coefficient of S and constant terms.
Yes, very good. So we'll compare this and then get A and B. So the two equations I'll write, you solve and tell me what is the expression for A, what is the expression for B. So once you calculate this, you will get something like this. A plus B equal to
It's only
3.
two terms, right, sir? A by S plus 8 and B by S plus 3.8.
Sorry, S plus 8, sorry. Yeah. 8 by S plus 4, yeah, Nandini. 8 by S plus 4. Which one? Okay, maybe you have mentioned previously. Sorry, A by S plus 8. Yeah. Thank you, Chandrasekhar, for pointing out. So A plus B is 3.333, and then you have 3.3333A plus 8B equal to 0. So now can someone tell me what is the value of A and what is the value of B? So I have already done. You just whoever has not done, please do, and everyone should do. Shamita, are you doing?
Yes, sir.
Okay, I'll just give 2 minutes time. Everyone, please do the calculation by yourself and tell me what is the value of A and what is the value of B.
Show the previous slides on me.
Okay, so has anyone solved?
Sir, is it A equal to minus 0.78?
No, then
B
you are
equal to
making some mistake.
0.29.
Yeah, please check because I am getting a different answer. So once you get AB, you substitute in A plus B equal to 3.333 and the other equation and check whether it is validating or not. So Parvatam says A 5.7. Yeah, you are right. A is 5.7. And B?
B it's 2.3.
Minus 2.38, right? Because A plus B is 3.33. Yes, sir. B is minus 2.38. Yeah. So now if I write the equation, I'll have A is 5.714 by S plus 8 plus B is minus 2.38 by S plus 3.3333. So can anyone tell me the time domain expression of I21 of t? The Laplace domain is there. I want the expression in time domain.
5.714 e to the power of minus 80
Okay.
U of
Then
t,
mhm.
U of t
U of t. Oh, I'll write the U of t for both at the outside. Okay.
minus 2.38
Hmm.
e power minus 3.3 t.
T whole into U of t. Yeah, very good.
Yeah.
So everyone is getting the same expression. Hello, Shamita,
Yes,
Nandini.
sir. Yes, sir.
You are getting same expression? Chandrasekhar, Meena, Parvatam.
Yes, sir.
Yes.
Please repeat that the main comparison line, sir.
Okay,
Both
this
networks have compared, right, sir?
one or which one?
No, sir. No, sir. Previous. No, sir.
This first one.
Yes, sir. Yes, sir.
Okay. So, okay, I'll just summarize. Entire problem again. First, let us check the answer. So they're asking e to the power 80 coefficient is a. So we have a is nothing but 5.714. So a is 5. Let me zoom in. A is 5.714. Yes, in the range. And what is B? B is the other coefficient. And alpha is the exponential. So B we got minus 2.38 if I'm not wrong. Minus 2.38. So minus 2.38 in the range. And alpha we got minus 3.333. But if you see, they have mentioned minus alpha. So alpha is 3.333. So let us go and check. Alpha is 3.333. So let me just also write. So we got A, B, alpha. So A is 5.714, B is minus 2.38, alpha is 3.333. So if we summarize this question, they have given the same network with different connections, and they are asking use Tellegen's theorem in Laplace domain and find this AB and alpha. So we know that Tellegen's theorem, the voltage of the first network multiplied by the current of the second network, but polarity should be same when you are solving the circuit. So I have considered this polarity because it is looking like a two-port network. So currents are entering and voltage is positive at the top. There is less than a minute. If this meeting ends, kindly join back. So voltage of the first source here, it is V1 of S, V1 of S. And the current of the second source, it is negative because it's in the opposite direction, minus I21 of S. Then the voltage of the second branch is 0. So this term vanishes. So this term vanishes. And then now LHS is done. Now coming to the RHS side, voltage of the second terminal, which is 1 ohm into I21 of S. 1 ohm into I21 of S into current of the first branch, which is I11 of S. I11 of S. Second term is coming from this one, the voltage of this, which is V2 of S, and current is in the opposite direction, minus I12 of S. V2 of S into minus I12 of S. I think this meeting will end soon. Please join back. Then we have substituted it, manipulated it. Then we have substituted the Laplace expressions, which we got from the given data, and then we have manipulated it to get I21 of S. So we have applied partial fractions, and then we got this term, and then we have compared. So the main crux of the problem lies in writing this expression. If you make any mistake here, then your entire answer will be wrong. So you have to be very careful while writing that expression. So Parvatam, is that clear? You are asking, right? This expression.
Sir, that line, please repeat, sir, that line.
This line.
Yeah, yes, sir.
Okay, so we are basically on the LHS side, we have voltage of the first network multiplied by the current of the second network. So one voltage is V1 of S here, other voltage is 0. This voltage corresponding current is minus I21 of S. Because this is 0, its corresponding current we need not consider. So on the LHS side, we have one term, which is the voltage of the first network multiplied by the current of the second network, which is V1 of S into minus I21 of S. Is this expression clear? How we are getting?
Yes, sir.
And 0 also clear, right?
So in that second network, there is no voltage source. That's why we have put 0, right, sir?
Because it is shorted, the voltage is 0. This voltage is 0, right?
Yes, sir.
So that's why we get the second term 0. Now coming to the RHS side, which is the voltage of the second network multiplied by the current of the first network. So here, this voltage, this current, this voltage, this current. So this voltage is 1 ohm into I21 of S, and this current is in the same direction I11 of S. So 1 ohm into I21 of S is the voltage multiplied by the current I11 of S. So is this expression clear?
Yes, sir.
Okay. Now this voltage, this current is over this voltage, this current. This voltage is V2 of S. This current is in the opposite direction. So minus I12 of S. V2 of S minus I12 of S. Is this expression also clear?
Okay, yes, sir. Clear, sir.
Okay. So then we'll proceed to the next problem if you don't have any doubts. So next problem is they are actually giving hints, so which is good thing. So the problem is solved using the compensation theorem. Okay, so this is our problem one, question one. This is our question two. Okay, so this please read the question first, then we'll proceed to solve. Have you read the question? So they have given one circuit where R is 4 and I1, I2 are known. Now they are saying if the resistance R is changed to 15.05, so it's like R plus delta R is 15.05 and everything remains same. And then I1 has become I1 plus delta I2 has become I2 plus delta I2, I3 has become I3 plus delta I3. Then they are asking what is the new values of that I1, I2, I3, which is I1 plus delta I1, I2 plus delta I2, I3 plus delta I3. So they are asking this. Let us go back to the theorem that we have learned, which is the compensation theorem. So whenever there is I plus delta I, that change, say only this resistance is changing, then in order to calculate this delta I, first we have to remove all the sources and this impedance will be connected something like this. Agree, everyone? You remember this, right? That we have discussed today. Yes, sir. Okay, so can anyone tell me in the original circuit what is the value of I3? Original circuit.
I1
Sorry, your voice is breaking.
I1 plus I2, sir.
Yes, sir. Sorry. Yes, which is value? Twelve ampere. Yeah. So I3 is 12 ampere. Similarly, whatever they have given, I1 is 4 ampere, I2 is 8 ampere. Now, what is delta R value? Delta R. What is delta R? Anyone?
11.05.
Yes, 11.05. Very good. So now I got the idea of what I need to have, because I need to have Z plus delta Z, which is given. I delta Z because I know I and I know delta R. So I can draw this circuit. So what happens to these voltage sources in this circuit? So for calculating, so in this circuit, we have to do something to the voltage source, right? Short circuit. Yeah, Jnanendra Singh is saying short circuit. Yes, they're shorted. So let me short E2 and E1 and redraw the circuit. So now the circuit that we have to solve has 9 ohm, 11 ohm. But here we have one resistance plus one voltage source. Okay. So this is 9 ohm. This is 11 ohm. So what will be the value of this resistance? What will be the value of this resistance? Anyone from the given data?
15.05.
15.05. Very good. 15.05 ohm. And what will be the value of this voltage source? Anyone? This is the given data.
It's 12 into 11.04.
Yes,
05.
very good. 12 into 1.
180.6, sir.
What did you do? Which two did you multiply?
12 into 15.05, sir.
Why did you multiply by 15?
Current into total impedance.
Current into
Volt impedance, sir. Total
which
impedance. Like
I into delta Z, right? What is delta Z?
delta Z is 11.05.
Yes. So now what will be the value? I is how much? 12, right?
Yeah.
Yeah. So how much you'll be getting?
180.6.
11. No, you made a mistake. So I asked you,
Okay.
that's why those questions. You have multiplied with 15.05, right? Not 11.05.
Yes, sir.
So 132.6 you will get, right?
The 12 into 15.05, sir.
No, that's why I have asked.
12
now.
into
12 into
Is
11.05,
it
right?
okay? Okay, sir.
Because it is delta R, not R plus delta R. This term you are seeing, right? This term, I delta Z. You got it? Your mistake?
Yes, sir. Got it, sir. Got
Okay,
it.
okay, okay. So this is the voltage. Now I have to calculate current. So first of all, direction of the current will not change. So this is delta I1, delta I2, delta I3. Okay. So the current direction is delta I1, delta I2, delta I3. Okay. So first, what we can do is reframe the circuit. 9 and 11 ohm are in parallel, right? So if they are in parallel, what will be the effective impedance? Anyone? If we redraw the circuit, 9 and 11, what is the effective impedance?
Four 4.95.
4.95. Okay, so this is our 4.95 ohm. So now can anyone calculate what is the value of delta I3?
Six point six three, sir.
How much?
6.63.
6.63
Yes, sir.
plus or minus?
Minus, sir.
Minus 6.63 ampere. So everyone is getting the same expression or any confusion, different answers you are getting? Shamita, are you following?
Yes, sir.
You got this expression?
Yes, sir.
Okay. Everyone got the same value? Yes, sir. Okay. So now we know, can you tell delta I1 in terms of delta I3? Anyone? What is the value of delta I1 in terms of delta I3 and delta I2 in terms of delta I3? in terms of 9 ohm, 11 ohm, because current is being divided, right? Delta I1 and delta I2.
Sir,
Delta I1 is
delta I1 equal to
Huh?
11 by 20
Hmm.
multiply delta I3.
Okay. And delta I2?
9 by 20 into delta
Okay.
I3.
Okay. Now can someone calculate the values and tell me?
Sir, delta I1 is minus 3.646, sir.
Okay. Delta
Delta
I2?
I2 is minus 2.98, sir.
Okay. Very good. So they're asking what is the new values. So the new values is I1 plus delta I1, I2 plus delta I2, I3 plus delta I3. So let us copy these values, whatever we got. So this is I1, I2, I3. And yeah, so now I want these values. I want I1 plus delta I1. So someone please calculate and tell me I2 plus delta I2 and I3 plus delta I3. I1, I2, I3, delta I1, delta I2, delta I3, all are calculated. You just have to
0.345.
0.34,
0.354.
0.354. Okay, very good. 0.354. And then
4.35, sir.
4.35. Which one? I2.
I2.
I think made a mistake.
Sir, 5.02.
Yes, 5.02. And I3.
5.37, sir.
So these are the final values. So you have to check in the question whether they are asking the change or the final values. We got the change because solving that circuit will only give the change. Now, if you see why compensation theorem is helpful, because they have changed one R and we need not even calculate E1, E2 and solve the entire circuit. We have gotten one circuit which is very simple to solve, right? Because there is only one voltage source, resistor parallel connection we have done, and we got delta I3. And by using this current division formula, we got delta I1, delta I2. So we already got the change. So this is the final value. So if you see, we have barely did any calculation, just small simple circuit rather than solving the entire circuit again. If you solve the entire circuit again, you will still get the same answer. Maybe that you can consider as homework and you can try and see whether you're getting the same answer or not. But if you see this using this theorem, because it's a result, it will simplify things. But only you have to understand when you have to apply compensation theorem. However, they have given, I'm not sure whether they'll be giving that in the final exam or not. Probably they'll give, but you should understand which theorem to be applied where.
Sir, when we are changing Z to Z plus delta Z,
Yes.
so how much the value of Z plus delta Z?
This is applicable. If you see here, they are changing from 4 to 15.05. So this theorem is applicable. Delta Z can be more or less, anything fine.
I want to ask that how much value we are putting in this particular question.
Delta Z.
Just check the values.
Which value?
Z plus delta Z.
You tell me what is Z plus delta Z in this question.
That is 4 plus 11.95, I think.
4 plus 11.05, right?
Yes, sir.
So R plus delta R is 15.05. R is 4. So delta R is 15.05 minus 4, which is 11.05, which is what we have written.
Yes, sir. Got it.
Now let us go and see whether our answers are matching or not. So I1 plus delta I1, which is how much we got? 0.354. 0.354 in the range. I2. I2 plus delta I2 5.02. 5.02 in the range. And I3 we got 5.37, which is also in the range 5.37. So any questions or any doubts until this point?
No, sir.
Okay. And we'll solve the next problem. I'm not sure why they have given this problem in this week, because if you see, this is just nodal analysis, nothing related to like what we can do in this week. It is just simple. So I'm not solving this because similar problem we have already solved and it has got nothing to do with the theorems. So like it is very straightforward. IA, IB, IC and VM they have asked. So you have to calculate IA, IB, IC in terms of VM, and summation of currents is 0, calculate for VM. It is just calculative, but however, it's a bonus to be given in this week because this is very simple and straightforward. And it is not related with the theorem, so let us not do that. Instead, we can solve a different problem utilizing the time. Okay, so this problem, let me copy paste so that you can give it a read and then we can solve. So this will be our question 3 for today. So someone has mentioned in the chat. Sir, please just brief so that we can do. Okay, Chandrasekhar. So they are saying this is the circuit and they are asking what is the value of Vm with respect to N, what is Ia, what is Ib, what is Ic. So now what you have to do is in this question, or the best way to do is I'll put it in my answer copy so that as it will be uploaded, you will have the access to this. Okay. So let me take this to the next page. So this will be our question 4. This will be our question 3. So what they're asking is find the value of IA, IB, IC. So basically what you have to do is neutral means ground, right? So this is a ground by reference point. You know this voltage, 200 angle 45. You know this voltage. You know this voltage. And unknown is Vm, right? Say this is my ZC. This is my ZA net impedance. This is my ZB. Apply KCL at this Vm. So you
M
will get
should be grounded, no, sir.
why?
All currents are flowing towards M.
So that voltage will be 0. Hello. Hello.
Once your voice is break.
Okay. So I'm saying neutral is ground, right? In any question, wherever there is voltage. So this I'm considering ground. Why are you saying Vm needs to be grounded?
All currents are flowing towards M, no, sir.
Okay. So the KCL says that summation of the current will remain equal to 0. But how can you say that this voltage has to be 0? It can be non-zero voltage also, right?
Okay, sir.
No, like you, not okay. Like you have to understand. Like, is it clear or like any confusion or like current summation of currents will be 0, but voltage need not be 0, right? Because no theorem says that if currents entering a terminal is 0, the voltage is 0.
Then all currents are coming from N terminals, no, so how can it be grounded?
No, this is a reference terminal. This is like neutral is always a reference terminal. Neutral is like a reference in this circuit. So this voltage they're giving with respect to this neutral terminal, which is often considered as ground. This is not ground because the current summation is 0. This is the reference for these voltage sources, which is mentioned as neutral. Neutral means a ground terminal. Like that is the convention. Like if we have RYB delta, then you have ABC and neutral. Neutral is ground. Neutral means 0.
Once again,
Like the convention is neutral terminal is ground terminal.
We can take M also grounded, Master.
Okay. Okay. If N is considered as ground, can we consider M also as ground?
No, sir.
No, right? But already N is given as a ground because neutral is always ground. In any circuit, neutral means ground. Like that is the convention we follow. Like we have ABC and neutral, right? So in star connection, we have ABC and neutral. So this is the star connection. So this is A, so this is B, this is C, this is neutral, which we consider ground. So this is the convention that we consider. So that the voltages are with respect to the neutral, which is often ground. So that's why N is already given as ground. Is that clear or?
Yes, sir.
Okay, sir.
Okay. So now if you apply KCL here, then you have
Just
you will
brief
get,
us so that we can perform.
yes, I'll give you
Because
the
we have.
demonstration.
Yeah, okay, sir.
VA minus VM by ZA plus VB minus VM by ZB plus VC minus VM by ZC equal to 0. This is the KCL, right? At M, because this current, and this current summation is 0. So now in this equation, only unknown is VM. So solve for VM. And once you solve for VM, then you can solve for IA, IB, IC. Clear?
Okay, sir. Okay. Thank you.
So
Sir,
this
we have
will
to
be
take
also updated.
VS 2045 and VBS 200,
Angle
200,
165. Yes.
Yes. Okay, sir.
Okay, I'll also give you the answer so that you can verify. So VM, IA, IB, IC. So these are the answers that you'll be getting. I have solved and I'm writing 100 angle 45 degrees volt. And then this is 1.975 angle 54 degrees ampere. All of you, please try this sum during your leisure time because it includes
Sure,
so many calculations so that it can also be like an experience or like a practice because it has so many calculations you might make mistakes. So once you solve this without any mistakes, then you can be a little bit confident that yeah, you are comfortable with the calculation. Okay, now coming to our question 4, just give it a read. You read this question? So the open circuit voltage between A and B is given by VAB. And if the terminals are shorted, and then the short circuit current is given by IAB. Now they're asking if we connect RAB there, what will be the current through RAB? And they're saying Thevenin's theorem in Laplace domain should be used. So what is Thevenin voltage here and what is Norton current here?
So Thevenin voltage is VAB, sir.
And okay.
Norton's current is IAB, sir.
Yes, sir.
And
Very good.
RL is RAB.
Yes, very good. So let us go through this Thevenin's equivalent circuit. Okay, so let me just draw this. So I need VTH and I need ZTH. So they have given VTH, but they have not given ZTH. So how to calculate ZTH?
Yes, sir. V by I, sir.
Yes, very good. So now let us convert this into Laplace domain. Yes. So, but we have to do in Laplace domain. So VTH of S is what? 25 into
25 by S or 25 1 by S minus 1 by S plus 1 by 2.
1 by 4.
1 by 4, sir.
Yes. So if you simplify this, you will get 25 into 1 by 4 by S into
by S into S plus
plus
1 by 4.
1 by 4. Yeah, very good. Now, if you do that
And
for
IAB
Norton, yes, what you will be getting?
is 4 by S, sir.
4 by S. Yeah, very good. Now, I have to calculate
RTH is,
ZTH.
and that is VTH by IN, sir.
Yes, VTH by I Norton. So Z Thevenin of S is nothing but V Thevenin of S by I Norton of S. So if you do that, you will get 24 by 16, 25 by 16 into S plus 1 by 4.
1 by
I've
4.
just skipped.
Yes, sir. Okay, okay, sir.
Now this is the equivalent circuit, right? So they're asking what is the current through RAB. So this load current is what they're
IL.
asking, IL. So what is IL?
IL
IL
is
of S is
VTH by
ZTH, ZL, right?
VTH Z plus ZL, sir.
So I load of S is nothing but VTH of S.
VTH by ZL plus ZTH plus ZL.
Yes, ZL. Yeah, very good. So let us get back. What is VTH? VTH is this 25 into 1 by 4 by S into S plus 1 by 4 into 1 by ZTH plus ZL. So what is ZL?
ZL is 10, actually
10, right?
10 by S.
No, not 10 by S. It is 10 because resistance is resistance only.
Yes, sir. Yes, sir.
Yeah. So resistance is resistance. So I'm putting in different color so that you will see that it will not change. And then ZTH is 25 by 16 into S plus 1 by 4. 1 by 4. So now if you simplify it, you will get 25 into 1 by 4 by S into S plus 1 by 4. Here you will get 16 into S plus 1 by 4 by 16S. So 160S plus 40 plus 25,
10,
which is
160 by 4.
Which is
yes, sir. Okay, sir.
40 plus 25, 65. Clear? This step is clear for everyone? Others are also following, right? I'm not hearing anything from others. Shamita, Nandini?
Yes, sir.
Gyanendra? Yes. Parvatam? Yeah. So if you now check, so this S plus 4 will get cancelled. So now what I will be doing is, I will divide the numerator by 160 and then I'll divide the denominator also by 160 because I need the coefficient of S to be 1. So this is my I load of S. So all of you please do, because this is the way I am doing. It need not be the same, but you should do along with me. Don't like wait for me to solve. You can solve by yourself directly itself. So once you do this, in the numerator, you will be getting 100. And in the denominator, sorry, in the numerator, you will not get 100. In the numerator, you will get 0.625. You will get 0.625 by S into S plus 0.40625. Is this clear? Just check whether you are getting the same answer or not. I have divided by 160.
Yes, sir. Yes, sir.
Okay. So now what I will do is, I will multiply and divide by
partial fraction.
Yes. Instead of partial fractions, one thing I can do 0.40625 by 0.40625. I will tell why I am doing this. If I do this, and if I segregate this term, say I segregate this term and this term, and keeping the rest inside, I will get 0.625 by 0.40625.
B by S plus B form, sir. Okay, sir.
And then this is 0.40625 by S into S plus 0.40625, right? So the numerator that we have 0.40625, I can write it as S plus 0.40625 minus S. So that will become 1 by s minus 1 by s plus 40625. And then if you simplify, you will get this expression as 1.538 into 1 by s minus 1 by s plus 0.40625. Clear the simplification how we have done? Because because it is only two terms, it is very simple because one is s. Else we can do partial fractions also, which will also give the same. But this is just a straightforward step, so that's why I have done this. Everyone clear this math?
Okay.
Instead of using partial fraction, we can use this method.
Can do.
also.
Yes,
This method, because here it is straightforward, because one is s plus a. So if I write the numerator as a, I can write a as s plus a minus s. But if I have denominator s plus b and s plus a, then it might not be straightforward. But only when one term is s, it is straightforward, then you can use. Else you can do partial fractions also, but this just saves somewhat some time. So now what is the I1 of t expression? Sorry.
Without calculation also we can do this, sir. If
Yes,
you
without
use
calculation also. Yeah, it is simple. Like, so what is the IL of t expression? Anyone?
1.538 into u of t.
Okay. Minus
1.538 into e power minus 0.40625 t into u of t.
Very good. 0.40625
t into u
of t amperes.
Total you can write u of t. Yes.
So this is the final expression. Let us go and see what they have asked. So they have given a plus b into e to the power minus t by tau. So a is this coefficient, b is this coefficient, tau is the time constant. So what is a?
1.538 and b is minus 1.538.
And tau?
Tau is
T by
1
tau.
by 0.40625, sir. Actually.
Yes, can you calculate and tell me?
Yes, sir. It is 2.46, sir. Minus 2.46.
Plus, because they have given minus t by tau.
Yes.
Time constant is
plus
always
2.46.
positive.
Yes, sir.
2.46. Gyanand Singh also said 2.46. So let us go and cross check whether the values are same or not. Then I'll summarize. A is 1.538. A is 1.538 within the range. B is minus 1.538 also in the range. Tau is 2. How much we got? 2.46. 2.46. It is also in the range. So this question is simpler, but if they have not given Thevenin's theorem, then you should be able to understand it is Thevenin's theorem. So they have given Thevenin voltage, Norton current, not Thevenin impedance. Using that, we have calculated the Thevenin impedance, and then using the Thevenin equivalent circuit, you can also use Norton equivalent circuit. Maybe that you can consider as homework and try to do it using that method. You'll get the same. I am more comfortable with Thevenin's because it is impedance and voltage. Current and impedance is a little bit like not so comfortable for me. I usually proceed with Thevenin's theorem most of the time, so I am more comfortable. So that's why I have used this. But you can consider Norton's circuit as well as and solve it using that circuit. So we know the IL expression. So we have simplified. You can use partial fractions, or you can also use the method that I have covered here. Then I got IL of S. Then I have converted it into IL of T. So any doubts till here? Anyone?
Sir.
Yeah.
Sir, in Tellegen's theorem, we can also write the statement like the sum of powers across each element in the circuit may be 0.
Yes, like that is to some extent you are right, but it is not the power in that circuit because we are multiplying voltage of this multiplied by current of this. So
Actually,
like
I have
not the
read
power.
some other questions, so that's why I am asking you, sir.
Yes, that way also you can do like voltage into current.
Okay.
The net power
If
is
you
also
have
0.
the same two types of network, then we can use this way of solving.
But whatever you have
Okay,
said, that is also right. But
So
that is not
actually,
Tellegen.
which one we have to use, sir, in a prominent way?
Depends.
Statement?
Depends because voltage like net power consumed is 0, so that is one thing. But if you see the question that they have, they have two networks
two
and they're
networks. Yes, sir.
asking. So here now you know that because there are two networks, I cannot simply do this plus this. Instead, I have to do for both.
Okay, sir.
Okay. So,
sir, in the problem, actually, we have taken the voltage because the plus terminal is from I to 1. That's why we have taken a plus I to 1 into 1, I think.
yes. So first I have fixed the polarity. Then using this polarity,
Okay,
both the circuits should follow the same. So that's why I have fixed the polarity at the beginning.
Okay,
And
sir.
because current is entering this terminal, this is plus and minus.
Yes,
so the
sir.
voltage is 1 ohm into I to 1 ohm plus.
1 into I to 1, yes, sir. Okay.
So just to summarize, we have discussed about multiple network theorems. We have started with the substitution theorem. Then we went to Thevenin's theorem. Then we have gone to Norton's theorem. Then we have also discussed the compensation theorem. And we have discussed Tellegen's theorem. Then we have discussed about the reciprocity theorem. Although we have not solved all the problems on all the theorems, but we have covered majority of the theorems. We have solved one problem on Tellegen's theorem. We have solved one problem that covers compensation theorem. We have solved one problem that covers Norton's as well as Thevenin's theorem. Substitution theorem is just a modification, so it is not of a big deal. But we have not covered any theorem on reciprocity, but it is simpler, like similar to two-port network. Probably you can give it a try. If you face any difficulty, you can ask. Then we have solved a few problems on these theorems. So if you have any further queries, you can ask, else we can end this session. Any queries?
Sir, in the last question, if they didn't give Thevenin's theorem, how can we find to use which theorem?
So if they have not given Thevenin's theorem, then you have to see that they have given open circuit voltage, which is Thevenin voltage, and then short circuit current, which is Norton current. So there you should get some idea of, okay, this is Thevenin's voltage and Norton current. So either I'll proceed with Thevenin's theorem or Norton's theorem.
Okay. For every circuit,
there is less than a minute, so probably this
Thevenin's
meeting will
theorem
end. Once this meeting ends, you join back so that we can continue the discussion.
For every circuit, Thevenin's theorem is applicable, sir.
Yes, but it should be linear. But as this course covers only linear circuits, yes, it is applicable.
Yes, sir.
Maybe this meeting will end. We'll join back. So if you have any doubts, you can ask. So any more queries you have? Anyone? Shamita?
Yes, last problem that ZL is 10, right, sir?
Sorry?
The last problem is that L is 10, right, sir?
Which L? Which L? This one?
V Thevenin by R Thevenin, V Thevenin by Z Thevenin plus ZL of S, right?
ZL of S, yes.
ZL is, we have to take a 10.
10, because resistance is resistance same in the Laplace domain, whereas inductance will become SL and capacitance will become 1 by CS. Because the resistance remains same, right?
Okay, sir. So tomorrow also we have that network problem solving session is there,
Yes.
sir.
Yes.
And previously I told that with both the semiconductor fundamentals of semiconductor devices and this session both are conducted at the same time. I informed that persons that you have given a 2 mail ID, right, sir?
Yes.
That what they told we cannot change that based on the availability of PMRF only we have to do that. But tomorrow also we have the 2 sessions. Most of the sessions I couldn't understand. I couldn't attend, sir, because of the reason.
But one thing is, as this video is already available in YouTube, you can go through it because when we are asked to fix one slot, we'll put that slot according to our availability. Because I have TA duty on Wednesday and Friday, and I don't usually conduct it on weekends. I conduct it on Monday. So all my sessions for the last few years, I'm conducting Monday 6 to 8 because it is comfortable for me. Probably that student might also have comfortable time on Tuesday, so that's why he's conducting on Tuesday. But if you are unfortunately busy that day and you cannot attend, you can always go through the YouTube video. So that was the idea, so that even if some students miss, they can go through that video later as it is available on YouTube. But if you have questions, if you could not understand anything, you can always contact that person through mail ID, or you can mention in the comment section. So other subscribers or other viewers can address, or the student, like whoever is teaching, he himself or he or she themselves can address directly.
Okay, sir.
Sir, which book we should follow to have good hold on the subject? Yeah, there was some reference that I have given to someone in one of the comments, but I don't remember the name. So once I upload this video to YouTube, in the description I will mention the link or the name. So once this video is uploaded, you just check in the description of the video where you will find this. Is that clear, Jnanendra Singh? Once I upload the video, I'll probably upload it by today night, 10:30 I'm planning to upload. So in the description, I'll mention the reference, which you can go through. If I find the link, I'll give the link, else I'll give the name, which you can check. Is that okay, Jnanendra Singh?
Sir, is that book is professor's book, sir? Bhattacharya's
No,
is it that,
not
sir?
his, not his. Actually, for this course, his notes, whatever lecture notes that is available, that is more than enough. But I'll give some other reference book which people follow for network analysis. That is an additional knowledge, not mandatory. If you want to go through to just see and get more clarity, you are always welcome. But I usually refer to Tapas Kumar Bhattacharya's notes, which is really good. So I follow that before I conduct this session. So I go through those notes and solve the problems, which is fine. But it is always welcome to go through the reference books, because that will give additional knowledge. Also, yes, for more problem. Yeah, this is also one thing. Oh, can we follow fundamentals of electric circuits? Yeah, you can follow, but try to solve those problems which are covered in this course. If you solve some other problems which are not there in the syllabus of this, then that will not add any benefit as far as this course is concerned. So try to solve only those problems which are in the syllabus of this course. Else you will get knowledge, but that will not be beneficial for this course. So yeah, you have to understand that. Any other queries? Okay, thank you, sir. Yeah. Okay, then thank you. I wish you all the best for your assignment. Solve as many problems as possible. And whatever homework that I have given, you also try to do that and try to solve by yourself and be confident in the calculations. Try to not make more calculation mistake. If you have any query, you can mention in the chat box. I'll try to address. And I wish you all the best. See you again in the next week with week 8 problem solving session. And have a good night, all of you. Thank you. Thank you for attending. See you in the next week. Good night. Thank you.